So the next speaker in this session is Basak Alper. And Basak is going to show another example of one of the ways that both visualization and virtual and augmented reality are being used to support some of the particular technical challenges that we have at NASA. Basak has been researching data visualization and joined the lab about a year and a half ago. She's been actually going to be responsible for designing the uplink and downlink user interfaces for the Mars 2020 mission, and has been working on a research project to visualize the design of spacecraft trajectories with Jeff Stewart in the audience and a number of other folks who've been here. So I'll hand it over to Basak.
Hi, I'm Basak, and I'm a user experience researcher / data visualization developer in Scott's group. I wrote this down, so I had to repeat it. Today I will present an immersive VR application specifically designed for trajectory design in early phases of a mission. This project is an interdisciplinary collaboration between myself and virtual reality developers in the Ops Lab, Parker's colleagues, and Jeffrey Stewart and others in the mission design and navigation section at JPL. Our VR app simply reduces a trajectory into a set of control points, defining where the trajectory has to go through in space and in time. And the user views the trajectory with the HTC Vive headset, and they can pick one of these control points with their controllers and move them in 3D space. And as they are doing this, in the backend, a trajectory solver is recomputing a valid trajectory going through the new control points. So before going into the details of our application, I would like to touch upon the motivations of this project and how we perceive VR. And I want to make this distinction that when I was thinking about these applications, I didn't consider the VR applications, which are more like a space, like field of view filling large display, but rather as a 3D virtual world. Like all these applications are taking advantage of the depth, which is a natural affordance of virtual reality. So I kind of categorized the successful VR applications in these 3 themes. One is education and training. Using VR, we can put an untrained pilot inside a cockpit, so we don't have to worry about them crashing a plane. Or we can, let untrained doctors perform surgical operations. In the case of engineering, it can put the viewer inside a jet engine or building that does not yet exist. This is Protospace from JPL. It's a very good example of engineering and design application of VR AR. It lets engineers to design spacecraft parts and define procedures for their assembly. VR also is a very successful tool to visualize complex 3D structures such as brain fibers. Dan already mentioned this example. And it can be used to reconstruct remote sites like Mars or remote in time like ancient places. So I realize a lot of my talk is repetition, so if you take a break, I won't judge you. So in all these applications, the common theme is to teleport the viewer to an inaccessible remote place. So it's inside the jet engine or the Mars's surface. And let the user explore this space as intuitive as possible, with using intuitive interaction metaphors as possible. So trajectory design is an inherently 3D problem. However, current tools mostly focus on mathematical analysis and often provide 2D cross-section visualizations, which are very hard to understand the 3D geometries from these 2D cross-sections, or hardly allow any visual exploration. You just do your analysis, look at a static image, go back, do your analysis, and look at another static image. So let's take a quick look at the existing tools in what aerospace engineers use when they are designing trajectories. One of the common tools they use is Cosmographia. It has this load and view capabilities. It doesn't do anything, you cannot redesigning the trajectory, but it has cool features. It offers planet models, spacecraft trajectories and orientations, instrument field of views and footprints. It allows users to switch between these views. You can turn them on and off, but it's a visual display, like I said. It's just a load and view tool. So there comes next is Copernicus. It's a generalized spacecraft trajectory design and optimization system, and it's capable of solving a wide range of trajectory problems, such as moon and Earth-centered trajectories, transfers, tours, and all types of interplanetary asteroid comet missions. It has a very clunky GUI, and display quickly gets cluttered, as in this case. Mystic is another high-fidelity trajectory design and optimization tool which can handle n-body problems. It can be used to analyze interplanetary missions. One of Mystic's strengths is its ability to automatically find and use gravity assist, so engineers love it. But the way to modify it is through these very clunky MATLAB GUIs, and again, you only get 2D cross-section visualizations. Finally, Monte, this is the JPL's signature astrodynamic computing platform, supporting all phases of space mission development from early stage design and analysis through flight navigation services. It offers a rich set of packages which can be modularly used for orbit determination, flight path control, maneuver design, and so on. Ideally, users can create whatever visualizations they want through the scripting, but in reality, Monte has a very high, very steep learning curve, and the visualizations you can create are limited to the Python graphical libraries, which are not that great. You have to do everything from scratch, kind of. So we asked our collaborators to describe these tools. What are they good for? How efficient and flexible they are, when they get painful, etc. And we came up with this ranking system and placed these tools on a 3D space. And one of the things that is clear is that as the tools get richer and more complicated and flexible, they become harder to use. So one of the differences that we kind of provide here is the user-centered approach to design. We are a collaboration between domain experts and user experience researchers and designers. We can compute many things and do crazy things in VR, as we discussed earlier. Navigation with 6 degrees of freedom, teleporting people here, there. But do these things really help users achieve anything meaningful in trajectory design? So if it doesn't help the user achieve something in their mission design, we shouldn't provide that thing, and we shouldn't make the interfaces and interactions more complicated and cluttered. So we are just focusing on what is the task at hand, how can be done in the most simplest way, and we only focus on that and try to provide those tools only, and not clutter your interactions and displays, because they can get very quickly cluttered. And the analogy I want to give here is think of the websites that you looked at in the early 90s when people discovered hyperlinks. The whole page was full of links, 30 things that you can click on. Then we learned that, this doesn't work. People cannot find what they want to click. So we have to nest them. Then people started to nest in deep hierarchies. There were you should remember, there were menus you go over something, it unfolds into this thing, and it unfolds into something, and then again you cannot find where the damn thing that I clicked last. But now we learn how many menu items you can put on a web page, and how when you're in a different page there is a different menu, these context changes. So same principles have to come to VR domain. We don't have it as yet, and we kind of abuse the domain. And this is another point that is already touched upon. So this collaboration between the spacecraft, aerospace engineers and us has been easy at some points, not easy at certain other points because of this lacking like some lingua franca of data expression. So some of the data we get from them are like 500,000 lines in a very, very non-standard format. We couldn't kind of, you literally wrestle with this data for weeks to get it into a standardized format, and then it kind of slows you down a lot. And we are really emphasizing that why can't we just express trajectories in a standardized way? This way, we can actually change whatever the front end is whenever we need to, and we can also change the solver in the back end whenever we need to. So I'll quickly show a video capture of what. So right now we are looking at a trajectory around Jupiter, and the orange arrows are the delta V's, basically required energy required to keep that trajectory in that mode. And the user picked one of these control points and adjusted, so now it has a less of a delta V at that point. Now we are watching one of my collaborators how he's doing these things using the Vive controllers. The view here is like what he's seeing through his head-mounted display. Again, he's finding one of the high delta V points, updating it. As he's updating it, the solver quickly recomputing a possible trajectory, and he's replaying the animation. So this is really, really at an early stage. This is just like a proof of concept to show people what we can do with this VR application. I'll tell you in a bit our vision for this project. But before that, I want to talk more about why we wanted to do this in VR. And we've seen a lot of good examples, and these were all touched upon, but now I'm going to throw you some references. Some people were asking whether there were any studies, and also I'm going to mention a couple of studies. So the first benefit is, the one we all know. To be able to locate something in 3D space, stereoscopy is the strongest cue for you to determine the depth of an object. But then there are other kind of less known properties of VR. We are able to acquire spatial knowledge in VR in a way that more resembles to real world. So this graph here is from this paper, and it says, there is this exposure time, and this is like training transfer, basically knowledge transfer, like your spatial knowledge transfer. If you need to get yourself quickly familiar with a place, look at a 2D cross-section, which is essentially a map. But if you really need to build a detailed spatial mental model of a 3D space, then VR gives you a more real-life-like experience. The other benefit is, this is also mentioned by Wolfgang, the other benefit is the ability to shift focus in different depth planes. This is true, and it makes selection harder, but at the same time, it allows us to focus on different depth planes, so to avoid visual clutter. A study showed that if there is stereoscopy, we are able to read overlapping labels in 3D and imagine how it would help to view these complicated trajectories. So in the future, what we would like to go with this, before then I'll summarize the benefits. So increased accuracy in perception of the spatial temporal context, helps to disambiguate overlapping 3D geometry, interactive manipulation and redesign, and collaborative design, of course, mentioned by Scott. So in the future, we want to allow users to do more fine-tuned modifications. We talked about limitations of the 6 degrees of freedom, so maybe we can add some widgets using the dial. They can input more refined adjustments to control points. They can bring in additional data into 3D. They can solve very specific problems like reducing an eclipse duration or changing the footprint on a planet. Again, you know, additional overlays. And the ecosystem design. Again, we already talked about this. But we would like to have a seamless workflow between the desktop tools, which allows you to do detailed analysis. For instance, we don't envision this VR tool to be something like you start designing your trajectory from scratch. You always work on something that already you thought of, but you're fixing certain things or you're trying to explain it to your collaborators this, that. That's pretty much it. And I thank you for your attention.
We have a few minutes for questions from Basak, so if you have a question, just let either myself or Michelle know. We'll pass the microphones around. Maybe we'll
Basak, is there any mission already using this to plan the trajectory? Or is there any mission from GPL that is already using this to plan the trajectory, or this is fully experimental yet?
This is at an experimental stage right now, but we were like, this is a prototype we built, and we showed this to various people at JPL, and we raised some money to continue further development, so there is definitely interest in going forward.
I have a question, Basak, about, I realize it's still quite early, but I'm wondering if in the tests that you've been doing as you've been designing and prototyping with the mission designers, do you feel like you're seeing the benefits that you're hypothesizing? And have there been any surprises about the potential for people to be able to use the tool to accelerate different types of work process?
So definitely, you know, a faster iteration is one of the things. You know, as you're moving this control point, you see an immediate feedback, right? Oh, you know, I shouldn't move it this way because this delta V vector is growing. I should go the other way. If we wouldn't have this immediate visual feedback, it would be a way more slower iteration. This is one of the immediate benefits that we observed. And definitely being able to understand the spatial properties of the trajectory. When people first put the goggle on, there is generally, you know, aha moment observed. But, you know, like Parker was saying, there is nothing here that you cannot do on a, you know, 3D desktop view if you spend 10 minutes. We are only saying if you use tools like this, you can do the same task maybe in 2 minutes instead of 10 minutes. It's more like a performance increase rather than a magic wand to show you something you've never seen before. Yes.
I had a quick question of, can you imagine a version of this for classrooms where, you know, kids can calculate trajectories to Mars and stuff like that being released in the future?
Yeah, that would be so cool, especially to explain dynamics, like physical dynamics. Hey, if I move this control point here, I get an unstable trajectory, you know. You can quickly turn this into a training tool, and people, instead of remembering all the mathematical properties of the trajectories, people can remember, oh, you know, I moved that control point that way and it kind of crashed, or it couldn't compute a trajectory.
You mentioned, is this on? Yeah. You mentioned that at this stage it's mostly a speed up, but I mean, I can see that this could go well beyond that, and I'm just looking at, I guess maybe this is the great thing about working with space.
Yeah.
You have a lot of space here. And but there's a lot of screen real estate, if you will, for you to add additional information and additional variables on the trajectories, and maybe even previews of options for moving.
Yeah, exactly. I kind of fast forwarded that section, but once you're looking at the trajectory, there is actually a lot of additional information that you want to bring in. You know, how much of this instrument I'm using as I'm cruising over this trajectory, or what are my communication windows with spacecraft stations. So, but it's all centered around this 3D spatial view.
Yeah.
But definitely you should bring in additional information, basically putting things in the same visual reference frame, right?
Yeah. I wonder if that might be something we could think of as a potential advantage of VR. We might call it something like increasing the richness of the display, and here you actually have the space to do that, I think. So that'll be really fun to see in the future.